A P-N junction is a boundary or interface between two types of semiconductor material, P-type and N-type, inside a single crystal of semiconductor. It is created by doping, for example by ion implantation, diffusion of dopants, or by epitaxy. If two separate pieces of material were used, this would introduce a grain boundary between the semiconductors that would severely inhibit its utility by scattering the electrons and holes. P-N junctions are elementary building blocks of most semiconductor electronic devices such as diodes, transistors, solar cells, LEDs, and integrated circuits. They are the active sites where the electronic action of the device takes place. For example, a common type of transistor, the bipolar junction transistor, consists of two P-N junctions in series, in the form Na-P-N or P-Na-P. The discovery of the P-N junction is usually attributed to American physicist Russell Olive Bell Laboratories. A Shockley junction is a special case of a P-N junction, where metal serves the role of the p-type semiconductor. Properties of a P-N junction. The P-N junction possesses some interesting properties that have useful applications in modern electronics. A p-doped semiconductor is relatively conductive. The same is true of an n-doped semiconductor, but the junction between them can become depleted of charge carriers, and hence non-conductive, depending on the relative voltages of the two semiconductor regions. By manipulating this non-conductive layer, P-N junctions are commonly used as diodes, circuit elements that allow a flow of electricity in one direction but not in the other direction. This property is explained in terms of forward bias and reverse bias, where the term bias refers to an application of electric voltage to the P-N junction. Equilibrium. In a P-N junction, without an external applied voltage, an equilibrium condition is reached in which a potential difference is formed across the junction. This potential difference is called built-in potential. After joining p-type and n-type semiconductors, electrons from the n region near the P-N interface tend to diffuse into the p region. As electrons diffuse, they leave positively charged ions in the n region. Likewise, holes from the p-type region near the P-N interface begin to diffuse into the n-type region, leaving fixed ions with negative charge. The regions nearby the P-N interfaces lose their neutrality and become charged, forming the space charge region or depletion layer. The electric field created by the space charge region opposes the diffusion process for both electrons and holes. There are two concurrent phenomena, the diffusion process that tends to generate more space charge, and the electric field generated by the space charge that tends to counteract the diffusion. The carrier concentration profile at equilibrium is shown in Figure A with blue and red lines. Also shown are the two counterbalancing phenomena that establish equilibrium. The space charge region is a zone with a net charge provided by the fixed ions that have been left uncovered by majority carrier diffusion. When equilibrium is reached, the charge density is approximated by the displayed step function. In fact, the region is completely depleted of majority carriers, and the edge between the space charge region and the neutral region is quite sharp graph. The space charge region has the same magnitude of charge on both sides of the P-N interfaces. Thus it extends farther on the less doped side in this example. Forward bias. In forward bias, the p-type is connected with the positive terminal and the n-type is connected with the negative terminal. With a battery connected this way, the holes in the p-type region and the electrons in the n-type region are pushed toward the junction. This reduces the width of the depletion zone. The positive potential applied to the p-type material repels the holes, while the negative potential applied to the n-type material repels the electrons. As electrons and holes are pushed toward the junction, the distance between them decreases. This lowers the barrier in potential. With increasing forward bias voltage, the depletion zone eventually becomes thin enough that the zone's electric field cannot counteract charge carrier motion across the P-N junction, as a consequence reducing electrical resistance. The electrons that cross the P-N junction into the p-type material will diffuse in the near-neutral region. Therefore, The amount of minority diffusion in the near-neutral zones determines the amount of current that may flow through the diode. Only majority carriers can flow through a semiconductor for a macroscopic length. With this in mind, consider the flow of electrons across the junction. The forward bias causes a force on the electrons pushing them from the N side toward the P side. With forward bias, the depletion region is narrow enough that electrons can cross the junction and inject into the P-type material. However, they do not continue to flow through the P-type material indefinitely, because it is energetically favorable for them to recombine with holes. The average length an electron travels through the P-type material before recombining is called the diffusion length, and it is typically on the order of micrometers. Although the electrons penetrate only a short distance into the P-type material, the electric current continues uninterrupted, because holes begin to flow in the opposite direction. The total current is constant in space, because any variation would cause charge buildup over time. The flow of holes from the P-type region into the N-type region is exactly analogous to the flow of electrons from N to P, therefore, the macroscopic picture of the current flow through the diode involves electrons flowing through the N-type region toward the junction, holes flowing through the P-type region in the opposite direction toward the junction, and the two species of carriers constantly recombining in the vicinity of the junction. The electrons and holes travel in opposite directions, but they also have opposite charges, so the overall current is in the same direction on both sides of the diode, as required. The Shockley diode equation models the forward bias operational characteristics of a π/N junction outside the avalanche region. Reverse bias. Connecting the P-type region to the negative terminal of the battery and the N-type region to the positive terminal corresponds to reverse bias. If a diode is reverse biased, the voltage at the cathode is higher than that at the anode. Therefore, no current will flow until the diode breaks down. Reverse bias usually refers to how a diode is used in a circuit. The connections are illustrated in the diagram to the right. Because the P-type material is now connected to the negative terminal of the power supply, the holes in the P-type material are pulled away from the junction, causing the width of the depletion zone to increase. Likewise, because the N-type region is connected to the positive terminal, the electrons will also be pulled away from the junction. Therefore, the depletion region widens, and does so increasingly with increasing reverse bias voltage. This increases the voltage barrier, causing a high resistance to the flow of charge carriers, thus allowing minimal electric current to cross the π/N junction. The increase in resistance of the π/N junction results in the junction behaving as an insulator. The strength of the depletion zone electric field increases as the reverse bias voltage increases. Once the electric field intensity increases beyond a critical level, the π/N junction depletion zone breaks down and current begins to flow, usually by either the Zener or the avalanche breakdown processes. Both of these breakdown processes are non-destructive and are reversible, as long as the amount of current flowing does not reach levels that cause the semiconductor material to overheat and cause thermal damage. This effect is used to one's advantage in Zener diode regulator circuits. Zener diodes have a certain lower breakdown voltage. A standard value for breakdown voltage is, for instance, 5.6 eV. This means that the voltage at the cathode can never be more than 5.6 eV higher than the voltage at the anode, because the diode will break down euro, and therefore conduct euro if the voltage gets any higher. This in effect regulates the voltage over the diode. Another application of reverse biasing is varicap diodes, where the width of the depletion zone changes the capacitance of the diode. Governing equations, size of depletion region. For a π/N junction, letting and be the concentrations of acceptor and donor atoms respectively, and letting and be the equilibrium concentrations of electrons and holes respectively, yields, by Poisson's equation. Whereas the electric potential, is the charge density, is permittivity and is the magnitude of the electron charge. Letting be the width of the depletion region within the P side, and letting be the width of the depletion region within the N side, it must be that. Because the total charge on either side of the depletion region must cancel out. Therefore, letting and represent the entire depletion region and the potential difference across it. Where, because we are in the depletion region, and thus, letting be the total width of the depletion region, we get where can be written as, where we have broken up the voltage difference into the equilibrium plus external components. The equilibrium potential results from diffusion forces, and thus we can calculate by implementing the Einstein relation and assuming the semiconductor is non-degenerate. Where T is the temperature of the semiconductor and K is Boltzmann constant. Current across depletion region. The Shockley ideal diode equation characterizes the current across a p-n junction as a function of external voltage and ambient conditions. To see how it can be derived, we must examine the various reasons for current. The convention is that the forward direction be pointed against the diode's built-in potential gradient at equilibrium. Forward current, diffusion current, current due to local imbalances in carrier concentration, via the equation. Reverse current, field current, generation current. Summary: the forward bias and the reverse bias properties of a PA-N junction imply that it can be used as a diode. A PA-N junction diode allows electric charges to flow in one direction, but not in the opposite direction. Negative charges can easily flow through the junction from N to P but not from P to N, and the reverse is true for holes. When the PA-N junction is forward biased, electric charge flows freely due to reduced resistance of the PA-N junction. When the PA-N junction is reverse biased, however, the junction barrier becomes greater and charge flow is minimal. Non-rectifying junctions. In the above diagrams, contact between the metal wires and the semiconductor material also creates metal-Euro semiconductor junctions called Shockley diodes. In a simplified ideal situation, a semiconductor diode would never function, since it would be composed of several diodes connected back to front in series. But, in practice, surface impurities within the part of the semiconductor that touches the metal terminals will greatly reduce the width of those depletion layers to such an extent that the metal semiconductor junctions do not act as diodes. These non-rectifying junctions behave as ohmic contacts regardless of applied voltage polarity. See also, diode and junction diode, diode modeling, semiconductor, semiconductor device, N-type semiconductor, P-type semiconductor. Transistor, field effect transistor, bipolar junction transistor, alloy junction transistor, PA-Na-P transistor, Na-Pa-N transistor. Transistor transistor logic. Capacitance voltage profiling, deep-level transient spectroscopy, PA-N diode, solar cell, semiconductor detector, references. Further reading, Shockley, William. The Theory of p-n Junctions in Semiconductors and p-n Junction Transistors. Bell System Technical Journal 28, 435 a €489 doi, 10.1002 per joule 1538-7305.1949 TB03645X. Retrieved June 12, 2013. External links, http, www.youtube.com/ Watch V =took 3L9Q educational video on the p-n junction. P-n junction power guru, August, 2012. Olaf Duim, Elementary Physics of p-n Junctions, 2007. P-n Junction Properties Calculator, p-n Junction Lab free to use on nanohub.org allows simulation and study of a p-n junction diode with different doping and materials. Users can calculate current voltage and capacitance voltage outputs, as well. Theory of p-n diodes Dr. Vasilescu understanding the p-n junction, explains p-n junction in a very easy-to-understand language.